Swayam Prabha. Digital India. Educated India.
I welcome you all to lecture number 29 on the topic flow through heat exchangers. Before getting into the contents of this lecture, let's have a quick recap on what we have discussed in the previous lecture number 28. So, we have discussed the third mechanism of heat transfer, which is the radiation heat transfer, which takes place without the presence of a medium. Okay. So, we have seen the various terminologies like black body, what is the difference between absorptivity, reflectivity and transmissivity. So, the summation of absorptivity, reflectivity and transmissivity will be equal to 1. The governing law of radiation also we have seen, which is Stephan-Boltzmann law. Q is directly proportional to T power 4, that is the amount of the emissive power of a black body per unit time per unit surface area is directly proportional to the fourth power of the Kelvin temperature, that is the absolute temperature. So, the constant which is used to remove the proportional symbol is the Stephan-Boltzmann constant, which has a value of constant value of 5.67 in 10 power minus 8 watts per meter square Kelvin power 4. So, we have solved a numerical question also. There was one factor, or rather a concept which was introduced, that was view factor or configuration factor, which is the fraction of the energy radiated from the surface 1 and which is striking the surface number 2. So, that we denoted as F12. For a parallel long surfaces, the view factor is taken as 1. And we have solved numericals based on varying emissivities of two surfaces, E1 and E2 are different, and also E1 and E2 same surfaces remains the same for both the surfaces. So, that was the numerical which we solved. Now, let us go to the contents of the flow through heat exchangers. Introduction, applications, classification, the temperature profile. There are two methods of analysis of heat exchangers. So, in this lecture we will be focusing on LMTD method, logarithmic mean temperature difference method, then correction factor and few numerical questions. So, what is the need for studying the heat flow through a heat exchanger? See, the different heat transfer applications, the requirements are different. It is not the same. For example, if we take the size of the heat exchanger which is used for cooling an electronic component, so its configuration is different. So, it may not be a very big size, and the heat exchanger which is used to condense the steam in a power plant, so where the water is the cooling medium. So, that heat exchanger the size configuration is different. The heat duty or the heat load of that particular heat exchanger is different. So, it is not, so the requirements are different. According to the applications, the design also changes. Different heat transfer applications require different types of equipment or heat exchanger design. So, that is what I was explaining just now. Heat exchanger is, as the name indicates, heat exchange between two fluids. It can be liquid to liquid and liquid, it can be liquid gas, gas liquid, or between two gases. So, it is a device in which heat transfer takes place between the two fluids. The fluids are not mixed or it is not touching each other. Okay. In the heat exchanger, the cold fluid is heated from an inlet temperature of T1 to T2, and the hot fluid is cooled from. So, the cold fluid is heated while the hot fluid is cooled. So, when we say two fluids, it can be, as I mentioned before, it can be liquid and gas, or both can be liquids or both can be gases. So, what happens is, here there are 4 temperatures involved. One is the inlet temperature of the cold fluid and its outlet temperature, the inlet temperature of the hot fluid and its outlet temperature. So, two fluids, one inlet and one outlet, so that makes 4 temperatures. So, capital T is the symbol which is used for cold fluid. So, this is capital from T1 to T2. Wherever I am using T1 and T2, it refers to cold fluid. Wherever small letter T1 and small letter T2 are used, it refers to the hot fluid. conditions at the inlet and outlet. One refers to the inlet and 2 refers to the outlet. So, these are just few applications of the heat exchangers, not just the summary of all the applications, because you will find heat exchangers this in a refrigerator, air conditioner, it is used in aviation applications, power plants, automobile, radiator, the radiator in the automobile, food processing, waste heat recovery units. So, suppose if you take the steam power plant, the boiler accessories, air preheater, economizer, all these are heat exchangers only. Then cooling of electronic renewable energy systems. So, these are just very few applications which I have summarized and put it in a single slide. There are plenty of applications apart from this also. Classification of heat exchanger. According to the direction of flow, it is classified as parallel and counter flow. Okay. Then according to the construction, we can use shell and tube. Instead of tube, coil is used, the tube is replaced by a coil, then tube in tube, or sometimes we can call it like a double pipe. There is a tube inside in which fluid is passed through the tube, and there is another tube surrounding that one. So, there will be a gap, that is annulus portion between the first tube and the second tube. So, in that the second fluid will pass. So, there is a heat transfer. So, that is tube in tube. In case of parallel flow heat exchanger, so this is the direction in which hot fluid is entering. So, in this if you see the schematic, it is from left to right. So, this is hot fluid arrow, this is hot fluid. So, it is entering and leaving. The cold fluid is also entering and it is leaving. So, in case of parallel flow heat exchanger, the direction of flow of both the fluids are same. The other name for parallel flow is co-current flow heat exchanger. Okay, so, that is what I have mentioned here. Counter flow is just opposite to parallel flow heat exchanger. Here you can see the hot fluid. If you compare this schematic with the previous one, there is no change in the direction of the flow of the hot fluid from left to right. In the previous one, cold fluid was entering from the bottom and it is moving towards the right side. So, the direction of flow is same, whereas in case of here it is entering at the top. Okay. So, it can be the other way also, the cold fluid can enter in the tube portion and the hot fluid can enter this is the shell portion, this is called the shell portion. This is the shell portion and this is the tube portion. Okay. So, this is so here you can see the cold fluid is moving from right to left. So, these two are cold fluid and in between the fluid which is circulated through the tube, inside the tube, that is hot fluid. So, the directions are opposite, one fluid is moving in this direction, the other fluid is moving in this direction. So, such a flow arrangement is called counter flow type of heat exchanger. And whatever the explanation I have given, that I have transformed into a temperature profile. So, for parallel flow, so this is the hot fluid, okay, this is the hot fluid and cold fluid. So, if I write the temperature, okay, so hot fluid we are using the temperature T1, T2, let me again this one, cold fluid is heated from T1 to T2. For cold fluid is heated from cold to fluid, is hot fluid is cooled from cold fluid is heated from T1 to T2 and the hot fluid is cooled from T1 to T2. Anyway, based on this, if I plot this one, T1 to T2, this is T1, this is T2. Okay. So, this is T1, this is counter flow, hot fluid is cooled, cold fluid is being heated. So, this is T1, this is T2, okay, and the cold fluid is, this is the inlet temperature and this is the outlet temperature. We can take capital T for hot fluid or cold fluid and the other small letter t for the other fluid. So, there is no hard and fast rule. Okay. So, this is for explanation I have used for explaining the concept of this parallel flow and counter flow. I have used capital T for the cold fluid and small t for the hot fluid. So, let me write it here, capital T cold fluid and small t for hot fluid. Later in the numerical question, I would have interchanged this one. Cold fluid is small t, capital small t is cold fluid and capital T is hot fluid, because that is the symbol or letter which is used in the data book. So, I would have followed that one. So, there is nothing wrong, but I would advise you to follow uniformly. Okay. Capital T hot fluid, small t cold fluid, or vice versa. Suppose if you take a condensation process, okay, so let us draw this line. This is temperature, how this will be there. So, during condensation, okay, so there is a phase change process. So, this is constant temperature. Okay. So, the steam is coming, it is an isothermal process. So, this is condensation. Okay. So, suppose if we take and the heat rejected during the condensation process, when the steam condenses from vapor into liquid, or if it is a refrigerant vapor into refrigerant liquid. So, the condenser is cooled either by water or air. Okay. So, whatever the medium we are using, so its initial temperature will be less. After it has taken the heat, its final temperature will be more. Suppose, so that means, so this will be the profile, temperature profile. Okay. So, that will be the, let us use the same cold fluid is capital T. So, this will be T1, this is T2, because the cold fluid is heated, it picks up the heat during condensation process, whereas this one will be T1 is equal to T2, this is cold fluid, this is cold, this is hot fluid. So, this is condensation. So, this is the temperature profile for a condensation process. Like that for an evaporation process also. So, heat is flowing from the hot fluid to the cold fluid. Okay. So, this is the direction in which heat flow takes place, heat transfer takes place. So, this is similarly for an evaporation process. Okay. So, it will be, the arrow mark will be in the upward direction, So, let me draw that one also. So, this is capital T. So, this will be evaporation process. Okay. And during, what happens during evaporation, the fluid, it takes the heat, from the, so the direction of heat flow will be from here. Okay. So, suppose if you are cooling the water, initially water temperature will be more, but the final temperature of the water will be this one. So, the refrigerant removes the heat from the water, thereby it vaporizes, and again it is a isothermal process. Okay. So, it will be like this. So, here if you see by this one, the hot fluid is cooled, from T1 to T2. Okay. So, if you write this one, this will be T1, this will be T2, okay, and this will be capital T1 is equal to T2. This is evaporation process, temperature profile of an evaporation process. Okay. Now, let us quickly go through the LMTD method, that is logarithmic, LMTD stands for logarithmic mean temperature difference. Okay. So, the formula is Q equal to UA delta T, either delta T LM or LMTD. Delta T LM is logarithmic mean temperature difference, delta T is temperature difference, LM means logarithmic mean. So, logarithmic mean temperature difference. So, both ways we can write it, either LMTD, capital L, capital M, capital T, T and capital T, or delta T, and outside the bracket we have to write logarithmic mean temperature difference, LM. So, Q is the heat exchanged, U is the overall heat transfer coefficient. If you compare U with the H is also heat transfer coefficient, U is also heat transfer coefficient, but H is only the heat transfer coefficient due to convection. due to convection. But here it is convection. We can take suppose if we do not neglect conduction, conduction also is there. 1 by U is equal to the resistance due to convection due to, suppose if radiation effects are negligible, it is summation of convection and conduction resistance. Again, sometimes what happens when we use say the water as the cooling medium, okay, in case of this one. So, if the water is not of good quality, if it contains this one, it will corrode the tubes or the shell portion of the tubes of the heat exchanger. So, sometimes there will be deposition of dirt particles or dust particles, deposition of dirt or dust particles on the shell side or on the tube side. So, that is called, that will resist the that will increase the thermal resistance, that means the heat transfer rate will come down. So, that is called fouling resistance, that is called fouling. So, that is also taken into consideration in U, but if we neglect fouling resistance, that is on the tube side as well as on the shell side, then 1 by U will be equal to 1 by the thermal resistance due to conduction and 1 by due to the resistance due to convection. So, these equations are, these are all the derived equations, okay. LMTD, this is capital T1. So, here again, here I am taking for hot fluid, capital T is the hot fluid. This terminology is, until now I am using capital T for cold fluid and small t for hot fluid, okay. So, which here I have just changed, because these terminologies I have followed what is there as per the data book, as per the heat and mass transfer data book. So, capital T is hot fluid and small t is cold fluid. So, this is very important. Okay, these symbols, letters as per HMT data book, HMT data book, because we will be referring the data book while solving the problems, either by this LMTD method, and there is another method that is that I will discuss in the next lecture, NTU method. So, for both these methods we may have to refer some tables, some charts, okay. So, depending upon the nature of the numerical question. So, this is as per HMT data book, as per HMT data book. So, inlet temperature of hot fluid, capital T2 is outlet temperature of the hot fluid, small t1 is the inlet temperature of the cold fluid, and this is, there is one, this one. So, there is a factor called correction factor which is introduced when actually when we design the heat exchanger in reality. It is represented by the letter F. So, F also represents view factor or shape factor in radiation heat transfer, but in heat exchanger F refers to correction factor, So, that is, this is introduced to estimate the true temperature difference from LMTD. See, well, when we design this one, this is like theoretically we find okay, if 4 temperatures are known, hot fluid inlet outlet and cold fluid inlet outlet, if you know all the 4 temperatures, we can find LMTD for the parallel flow or for a counter flow, because this is the formula. These formulas I have taken from the HMT data book. Okay. So, this correction factor is used when we are designing a shell and tube heat exchanger or a cross flow heat exchanger. Cross flow heat exchanger means the heat transfer takes place when the fluids are flowing in one fluid is flowing like this, another fluid is flowing normal to the first fluid, that is perpendicular to the flow, perpendicular to the flow of the first fluid. So, this is like a factor of safety, this is like a factor of safety. Now, let us, with this theoretical background, let us solve numerical question, because this is like how to design the heat exchanger by LMTD method, how to design the heat exchanger by NTU method. So, in this lecture I will be focusing on LMTD method, and in the next lecture we will be continuing the heat exchanger from the viewpoint of analysis of heat exchanger by NTU method. So, in a condenser of a power plant, the steam condenses at a temperature of 60, the cooling water enters at 30 and leaves at 45. So, if you see the temperature profile, so this is, of course, here I have used for cold fluid T, but I will be using small t only. So, the cold water is entering the condenser at 30 and it is leaving at 45. So, the temperature profile is correct, whereas the steam temperature remains constant. It is a phase change process. Similarly, in the evaporation process it is a phase change process. So, this fluid remains constant and here it is this one. Okay. So, here it is like hot fluid, this is the cold fluid. Determine the LMTD of the condenser. It is a very simple numerical question. So, here I have taken again, let me remind, capital T is hot fluid, hot fluid is the one which will be cooled and cold fluid is the one which will be heated, and small t is the cold fluid. Okay, so, hot fluid is given, hot fluid is capital T1, because it is condensation, the temperature phase change process, there is no change in the temperature of the hot fluid, only there is phase change. Okay. So, T1 is equal to T2 is equal to what is the temperature 60, and cold fluid is water is entering at 30, it picks up the heat as a result of condensation process. When heat is added to a substance, its temperature will increase obviously. So, 45 degree centigrade. So, this is cold fluid. We cannot write small t1 equal to T2. Okay, that means if you are T1 equal to T2, that means there is no change in the temperature, that means the cooling medium has not removed any heat from the condenser during condensation process. It is clearly the condenser. Okay. So, let us write the LMTD formula, capital T1 minus, I have written this formula. So, that means I am assuming the flow to be, it is like a parallel flow. See here, if you see the diagram, this hot fluid is also moving in this direction, hot fluid, and cold fluid is also moving in this direction. Okay. So, this is the direction in which cold fluid is moving. So, both the fluids are in direction are same. So, it is parallel flow, parallel flow. So, same thing is here also. Let me draw the diagram so that you will easily understand. So, this is the temperature, this is the condensation process. Okay, so, here capital T1 is equal to T2 is equal to 60 degree centigrade. So, this is hot fluid, okay. This is small T2 which is equal to 45 degree centigrade, this is small T1 equal to 30 degree centigrade. So, the cold fluid is heated. So, that is why its outlet temperature is more than the inlet temperature, and the hot fluid in this case it is condensation process. So, it remains the same, otherwise T2 will be less than, capital T2 will be less than capital T1 cold fluid. Okay. So, both are in the flow takes place in the same direction. So, it is parallel flow. So, for a parallel flow, LMTD is capital T1 minus small t1 minus capital T2 minus small t2 divided by ln of this ratio, this first term divided by second term, T1 minus T1 divided by T2 minus T2. So, this is the formula, capital T1 minus small t1, that is temperature difference, the inlet temperature difference between the hot fluid and the cold fluid minus temperature difference between the outlet temperature of the hot fluid and cold fluid divided by the ln of this term divided by ln of this term. Okay, so, if you substitute, so here all the temperatures are given, T1, T2, everything is given. So, this is given, of course, T1 is equal to T2, small t1 and T2 are different. So, if you find LMTD comes to around 22 degree or 21.6 degree centigrade to be more specific. Okay. So, the why I am taking as a parallel flow means because the process, the flow, the direction of flow is same, it is in the same direction. If it is opposite, we can use the formula LMTD of a counter flow heat exchanger. Okay. So, this is a very simple numerical question. Next one, cold water flowing at 0.1 kg per second is heated from 20 degree to 70 degree. If there are two temperatures given, inlet temperature is less, outlet temperature more, means that is a cold fluid which is being heated. The source of heat for the cold fluid is the hot fluid. So, when there is a heat transfer, so the cold fluid will be heated, the hot fluid will lose the heat. This is the cold fluid is gaining the heat, cold fluid is gaining the heat from the hot fluid. So, the hot fluid temperature will, its temperature will drop, the cold fluid temperature will increase. And whenever in the heat exchanger, if you the principle is like one fluid passes in the shell, the other fluid passes in the tube, in case of a shell and tube heat exchanger. If it is a tube in tube heat exchanger, one fluid will pass in the inner tube, the other fluid will pass in the annulus between the inner tube and the outer tube, because there you will not have a shell portion. Similarly, if it is a shell and coil, one fluid will pass through the shell portion and the other fluid will pass through the coil portion. Coil, instead of tube, you have the coil. Okay. So, the rate of heat transfer is like first convection from the fluid, suppose if it is a shell and tube, from the fluid which is in the shell portion to the tube, that is convection. Then within the tube, that is conduction. Then again from the tube to the fluid, it will be convection. Okay. So, it is like convection, conduction and convection. So, let us this is a quite lengthy problem, let us use this one. I will be using the data book. Let me write the given data. Let us write, so there is a overall heat transfer coefficient is given, this is u value, this is given as u. So, it is if you write the data separately for hot fluid and cold fluid, it will be easy to understand and easy to work out the problem also. So, here the cold fluid temperature small t1 is 20, capital small t2 is 70. Okay. So, I have used small letters t. Okay. So, again here capital T hot fluid, small t cold fluid. So, this is cold fluid, small T1 is equal to 20 degree centigrade. After the cold fluid is heated, its temperature increases from 20 to 70 degree centigrade. Okay. Mass flow rate of the cold fluid is given. So, this is m dot. Okay. So, this is m dot. So, due to some compatibility, so this dot is not there is some technical issue in fact. So, m dot of the cold fluid is given 0.1 kg per second, m dot of the cold fluid is 0.1 kg per second, and the data given pertaining to hot fluid is mass flow rate is given, that is also 0.1 kg per second, and inlet temperature of the hot fluid is given. Inlet temperature of the hot fluid is T1 is equal to 90 degree centigrade, mass flow rate of the hot fluid is equal to the mass flow of the cold fluid, which is, so both the hot fluid and cold fluid quantity are same, which are circulated per second in terms of kg, that is same. Okay. M dot H is equal to m dot C. Let me tell you, if you want to solve the problem by LMTD method, we should find out LMTD, for which 4 temperatures are required. Here 3 temperatures are given, small t1, t2 and capital T1, but capital T2, the outlet temperature of the hot fluid is not given. So, the first step is to find out capital T2. Suppose if capital T1 and capital T2 are given, either of small t1 and t2 is not given, then we have to find out, without knowing all the 4 temperatures, we cannot find out the LMTD, whether it is for a parallel flow or for a counter flow. Otherwise, it should be a condensation process or evaporation process where one fluid temperature is same, because isothermal process, there is no change in temperature. it is only phase change, or it should be an evaporation process. If it is not an evaporation or a condensation process, then the T1, T2, T3, T4. Of course, T1 can be equal to T2, capital T1 equal to T2 in case of condensation, but we should know all the 4 temperatures. Now, in order to find out this capital T2, so we are going right, heat lost by hot fluid is equal to heat gained by cold fluid. So, the hot fluid is losing the heat and the cold fluid is gaining the heat. That means QH is equal to QC, and the basic formula is mCp delta T, mCp delta T. So, here I can write m dot H Cp of hot fluid and delta T, hot fluid delta T is capital T1 minus T2, which is equal to, for cold fluid I can write mass flow of the cold fluid, that is why you have to use the suffix very clearly, the subscript. H refers hot fluid, C refers cold fluid. Otherwise, if we write m dot and m dot on both sides, it is, we cannot differentiate which is the hot fluid and which is the cold fluid. So, m dot C into specific heat capacity of the cold fluid into cold fluid temperature difference is small T1, T2. So, the bigger temperature is T2 minus T1. Suppose here if I want to find this one, this I cannot find, I can find this one, I can find this QC because I know m dot C and the fluid used is water. Okay. Cold fluid is cold water, hot fluid is hot water, it is cold water, okay. And here also it is hot water, hot water. So, the moment we know the working fluid is water, we know the Cp value. So, therefore, Cp value of cold fluid is 4.18 kilojoule per kg Kelvin, Cp of and also it is hot water also it is same, okay, 4.18 kilojoule per kg Kelvin. Now, I will find QC, QC is equal to m dot C Cpc into T2 minus T1, because all the values are known, all the values are known. So, first step is to find QC, let me quickly go through it. Okay. So, QC is 20.9 kilowatt, 20.9 kilowatt. So, this is the amount of heat gained by the cold fluid from the hot fluid. So, heat loss is equal to heat gained. So, now I will substitute this one. So, this is nothing but heat lost by the hot fluid, which is nothing but m dot H Cph into T1 minus T2. Here, so this I know, whatever the heat gained by the cold fluid is equal to the heat lost by the hot fluid. M dot H is given, Cph we know Cp of specific heat of the water, T1 is given. So, the only unknown is T2. So, using this formula we can find out the outlet temperature of the hot fluid. So, if you calculate, you will get 40 degree centigrade. So, T2 is 40 degree centigrade. Okay. So, what is the type of heat exchanger it is given? It is counter flow. It is clearly given counter flow type heat exchanger. So, I will be using the LMTD formula for a counter flow heat exchanger. So, LMTD formula for counter flow, LMTD is equal to capital T1, there is no change in the first term, instead of small t1 it will be small t2 minus capital T2 minus small t1 divided by ln of capital T1 minus small t2, this ratio, this difference divided by this difference. So, this is the LMTD formula. If you substitute, you will get, we will get LMTD as 0. Okay. So, if you get LMTD is equal to 0 degree centigrade, LMTD. So, if you get LMTD 0, if you substitute Q equal to UA LMTD, Q equal to 0, that means heat transfer is 0, which is not true, because the hot fluid temperature has reduced from 90 to 40, that heat has been taken by the cold fluid, because of which its temperature has increased from 20 to 70. So, that means there is a heat transfer process has taken place. So, if we take LMTD 0, whenever LMTD is 0, it means, so this is very important, capital T1 minus small t2 or, okay, so let me, it means this is equal to this one. Okay, let me underline this clearly, otherwise the letters are not visible. So, that means temperature difference, capital T1 is the hot fluid inlet temperature minus cold fluid outlet temperature, or hot fluid outlet temperature minus cold fluid inlet temperature, that means it is same. Here it is same. If you substitute capital T1 minus small t2 or capital T2 minus small t1, it is delta 20. So, whenever delta T is equal to 0, we have to take this value, either capital T1 minus small t2 or small t, which which will be, literally it will be equal. So, delta T, therefore, LMTD is equal to 20 degree. Okay. So, if LMTD is 0, then LMTD is equal to capital T1 minus small t2, okay, which will be equal to capital T2 minus small t1. So, in this case it is 20 degree. So, we will take the LMTD as 20, substitute in the formula Q equal to UA LMTD. So, we have been asked to find out, estimate the required heat exchanger area. So, let me find out the area here. Q is equal to U into A into LMTD. This is without correction factor. Next, I will be comparing the results with the correction factor, okay, because here if you see, compare the results with that of a heat exchanger with 1 shell and 2 tube pass, compare the results with that of a heat exchanger with the 2 shell and 4 tube pass. So, then you will understand how much variation in the heat transfer area. So, this is Q, we know Q is 20.9 kilowatt, U value is given in the question, see U value is given as 2000 watt per meter square Kelvin. This is given, this is given. Okay, so, Q value is given, Q value is, this is the, if the overall heat transfer coefficient. So, that means it is given 2000, U is given. LMTD is 20 degree. So, area is equal to Q by U into LMTD. So, this comes to, if you calculate, 0.522 meter square, 0.522 meter square. So, this is the heat transfer surface area to achieve this process, Here U is in watts per meter square Kelvin. So, Kelvin into delta T, and Q is in watts. So, watts and watts will get cancelled, delta T temperature Kelvin and Kelvin will get cancelled. So, we will be having the area in meter square. Now, let us compare, let us take this one, compare the results with that of heat exchanger with 1 shell and 2 tube passes. So, whenever you are asked to find out the heat transfer area for like single shell 2 tube or single shell 4 tube, it will be in multiples of 2 only, even number, not odd number. Before that, you should know what is a 1 shell and 2 tube. So, this is here, see here, this is shell, this portion is shell, this is the shell and this is the tube. So, correction factor for plot for exchanger with 1 shell pass and 2 or 4 or multiple tube passes. So, here the fluid is going like this, that is 1 pass. Okay. So, 1 pass is like this, this is 1 pass. Okay. So, if it comes like this and goes like this, 2 pass, this is 2 pass. Okay. 1 pass, and again if it turns and I mean if it is going like this, it is 2 pass. Again if it takes one more thing, that will be 3rd pass, of course it will be in even number. So, then again it will be 4 pass. So, if you see the next one, see here, this is 1 pass, this is 2 tube pass, then it is coming again, this is entering the second shell, this is shell 1, this is shell 2, this is tube pass 1, tube pass 2, tube pass 3, tube pass 4. So, here this is for 2 shell 4 tube passes. It can be 8 multiples of, here it will be in multiples of this one, it will be in even number only, it will be in even number. Suppose if I have 3 shell, it will be 6 tube passes. Okay. Now, the same problem. So, here if you see this is the page number 167 from HMT data book, these graphs are available. So, whenever you are asked to design the heat exchanger, find out the heat transfer area or whatever, in case area is given, overall heat transfer coefficient is to be found out. Shell, single shell 2 tube passes or single shell or 2 shell 4 tube passes, whatever it is, we have to use this correction factor chart. So, here P is equal to this one. Again let me repeat here, capital T is hot fluid and small t is cold fluid. So, that is why I have used this some small t. So, we can, the x axis is P equal to, there is a P is a constant, small t2 minus t1 divided by capital T1 minus small t1. Similarly, here this is R, these are all R, R is equal to, it is written here. Okay. So, this is R, capital T1 minus T2 divided by, just we have to substitute the value. So, I am finding the value of P which comes around 0.71 and R value is 0.6. Now, this is for 1 shell and 2 tube passes. So, I will be taking the first chart, this chart, page number 167. So, if you see here, I have written here from heat and mass transfer data book, page number 167 for 1 shell pass and 2 tube pass. So, 1 shell pass, in shell there is 1 pass and in tube 2 passes are there. So, page number 167, page number 167. So, this is P value, okay, 0.7 and this is 0.6, this is 0.6, this is R, this is R, all these curves are R and this is 0.7. So, if you find this is the intersection point, this is the value, this is the correction factor. So, I am getting 0.5 is the correction factor, this is the correction factor from page number 167. Now, equation will be for correction factor, equation will be, okay, equation will be Q equal to UA LMTD, no change, UAMTD multiplied by the correction factor F, here F is the correction factor, F is the correction factor. So, the correction factor is 0.5 corresponding to, I have referred the chart which is in page number 167, that is for a single shell pass and 2 or more than 2 passes, tube passes. So, you can see the increase in the heat transfer area from 0.52 meter square, it is doubled than the previous one. Now, let us do a similar analysis for 2 shell and 4 tube passes. That means, I will be using the chart which is in page number 168. Again, here also the word tube is missing. So, let me edit it. Shell pass separately and tube pass. So, that is the appropriate way to represent. So, from heat and mass transfer data book, page number 168, page number 168. So, this is page number 168. Again, this is P value. Okay. So, this is P value, this is R value, these incline, these are all R value, these are all R value, these are all R value. Okay. So, there is no change in the P value and R value, only the chart is different, So, P value remains the same, previous P value is also same 0.71, R is 0.6. So, now in this chart I will find out where is 0.7, see P value 0.7 is here, this is the value, this is P value 0.7, R value 0.6 is this graph, this is 0.2, this is 0.4 and this is 0.6, this is r equal to 0.6. So, you have to find out from here the intersection point where it moves, So, this is the intersection point. So, it is coming somewhere else here, So, here f is equal to 0.92 approximately we have taken, 0.92. Similarly, in the previous chart f is equal to 0.5. Now, the correction factor has increased from 0.5 for single shell to 2 pass when we analyze the same problem for a double shell and 4 pass. So, the correction factor has increased from 0.5 to 0.92. So, if you substitute the heat transfer area it is slightly more than the case where correction factor is not there. Without correction factor it is 0.522. With correction factor for a single shell 2 pass it has doubled, the heat transfer surface area has doubled, and with 2 shell and 4 tube heat exchanger passes, so it is slightly more than 0.52, slightly more than 0.522 meter square. So, that completes the problem. So, these page numbers are different, that also I have marked it, and this is the HMT data book. Again the same, let me emphasize, it is the 9th edition published by the author C.P. Godan Raman and Subramanian. So, I think 2 more problems are there. This is the last problem in this one. Consider a parallel flow heat exchanger with area A suffix P, P refers parallel flow. So, let me again put emphasis here mass flow rate is m dot, So, let me use m dot here, otherwise it will be, this is m dot and here I have put m dot, mass flow rate is m dot, not m. So, let me again emphasize, if we want to solve the problem by LMTD method, we should know all the 4 temperatures. If 3 temperatures are given, mass flow rate is given, we can find either heat loss or heat gained. Once heat loss or heat gained is found, heat loss is equal to heat gained. So, we can find out the 4th temperature, the unknown temperature, either it can be capital T1 or capital T2, or it can be small t1 or small t2. So, parallel flow heat exchanger area is given, counter flow heat exchanger area is given. Parallel flow area is AP. The hot fluid is flowing at 1 kg per second from 80 to 50. That means, hot fluid is cooled from inlet temperature of 80 to outlet temperature of 50. Let us write this the given data. Let me first write the fluid data, then we will write this one. Hot fluid, and here let me write cold fluid. Capital T1 is 80, capital T2 is 50. So, again let me write it here. Capital T is hot fluid, small t is cold fluid. So, mass flow rate of the hot fluid is given 1 kg per second. So, m dot h 1 kg per second. So, this is the m dot, Cold fluid is this one. Mass flow rate of the cold fluid is given, that is also, if you see the question, the cold fluid is flowing at 2 kg per second. Inlet temperature of the hot fluid is 10 degree centigrade. The hot and cold fluid in both the heat exchangers are same. The hot and cold fluids in both the heat exchangers are same fluids. Overall heat transfer coefficient is same in both parallel and counter flow. We have to find out the ratio of area of counter flow to the ratio of to that of the parallel flow, that is AP by AC by AP. So, that means first let me write the given data completely. So, this is 2 kg per second and small T1, the inlet temperature of the cold fluid is given. So, we do not know here small T2. Capital T1 and T2 are known, small T1 is given, small T2 is not given, but We know the mass flow rate of this one. So, what I am doing is, we do not know what is the fluid. Let us assume that the fluid in both the heat exchanger to be hot and cold water respectively, hot and cold water respectively. That means, I can write the Cp of hot fluid is 4.18 kilojoule per kg Kelvin, and the Cp of cold fluid is also same, okay, water Cp. If the fluids are different, definitely we should know the Cp value, we cannot take 4.18. If it is air, we can take 1.005. Okay. Now, to find out T2, I should know Q. So, again the same concept, heat lost by the hot fluid equal to heat gained by the cold fluid. Because I know all the values for hot fluid, so QH is equal to m dot H Cph, hot fluid inlet temperature and hot fluid outlet temperature. All the values are known. So, if you substitute QH is equal to, let us quickly go to it, 125.4 kilowatt, 125.4 kilowatt. Now, this is the fluid heat gained by this fluid. So, QC is, we can write it as mass flow of the cold fluid into Cp of cold fluid into temperature difference of the cold fluid. Cold fluid outlet temperature will be more than the inlet temperature. So, this is nothing but this value. Okay. So, let me write it here. So, this is nothing but this value, because heat lost by the hot fluid is gained by the cold fluid. So, this is equal to this one, this we know, this we know, this we know. We can find the outlet temperature of the cold fluid. So, that will come around 25 degree centigrade. So, the cold fluid is heated from 10 degree centigrade to 25 degree centigrade. Now, first I will calculate the area for a counter flow, parallel flow, or it can be either way. So, now parallel flow, we have to find out the LMTD. For parallel flow, the LMTD, you use this formula. Okay. So, capital T1 minus small t1 minus capital T2 minus small t2 divided by ln of capital T1 minus small t1 divided by capital T2 minus small t2. Okay. So, this comes around 43.7 degree centigrade LMTD. Okay. Next, I am finding Q value, Q equal to UA LMTD, Q equal to UA LMTD. Okay. So, this is for parallel flow, because we have to do the similar calculation for counter flow also. So, LMTD for parallel flow, U is same, A is same. So, using this formula you can find UA, because it is given, we do not know the value of U, but U for parallel flow and counter flow both are same, both heat exchanger, the fluid are same, the heat transfer coefficient is same, but the area are different, areas are different. So, here this is AP, A suffix P means area of the parallel flow, So, if you find, we will get 2869.5, okay, watts per Kelvin, it is not in kilowatts, or 2.86 kilowatts per Kelvin, U into A. Similarly, for counter flow, we have to find out LMTD for counter flow. So, this is LMTD for parallel flow. So, the formula is capital T1 minus small t2 minus capital T2 minus small t1 divided by ln of capital T1 minus small t2, capital T2 minus small t1. So, using this formula, if you calculate, because now all the temperatures are known, LMTD is 47.2 degree centigrade. This is LMTD for counter flow. Apply the same formula, Q equal to U into A of counter flow, U remains the same. So, no need to write UP or UC into LMTD of counter flow. So, these two we know. Okay. So, therefore, U of into A of counter flow is equal to, the calculated value is 2656.8. So, this is equation number 1, equation 1. This is equation number 2. Okay. We have been asked to find out the ratio of counter flow to parallel flow. That means divide the equation number 2 by 1. Equation 2 divided by equation 1. So, that means first let me write the right side left side, u into AC divided by u into AP is equal to 2656.8 divided by the right hand side of the first equation 2869.5. 2869.5. U and U will get cancelled. So, if you calculate the counter flow area to the parallel flow area, it comes around 0.9. It is 0.92. So, this is the answer. This is the answer. So, let me conclude this one. So, in this lecture number 29, we have seen the types of heat exchangers, parallel flow, counter flow. This classification is according to the direction of flow. If both the fluids flow in the same direction, it is parallel flow. If it is opposite direction, it is counter flow. The other name for parallel flow is co-current flow. Then we can classify heat exchanger based on construction, shell and tube, shell and coil, tube in tube. We have seen the overall heat transfer coefficient, the basic formula used to analyze the heat transfer designed by LMTD method, that is Q equal to UA LMTD. There are two different set of formulas for LMTD, finding out the LMTD. Whenever there is a heat transfer area to be found out for a heat exchanger in which number of shell pass, number of tube passes are given, that means we have to find out the correction factor from the chart which is given in the heat and mass transfer data book. So, we have solved 3 numerical questions. One is finding the LMTD, one is finding the heat transfer area without correction factor, then with correction factor for 2 different conditions, single shell pass and two shell pass, and we have solved one more numerical question. So, with this let me conclude lecture number 29. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.